All right, so in this video, we're just going to continue looking at a few more examples with integration by parts. And in the last video, you saw that for the first time, we were now able to integrate a logarithmic function all by itself without having a u-sub opportunity. Same thing here goes for inverse trig functions. Okay, anytime you see these inverse trig functions by themselves, the only way to integrate them is going to be by parts. So to get started, we'll select our u and our dv. So using our ilate inverses to start, we do have an inverse, obviously. That's the whole point of this problem. The inverse cosine of 2x, and then everything else has to be the dv, so dx. Our du would be the derivative of this guy, so that's going to be negative 1 over the square root of 1 minus 4x squared back times the derivative of the inside, which is 2, and then we have our dx. So remember, the derivative for inverse cosine is the same exact as inverse sine except the negative. And then moving down to our v, that's just going to give us an x for that. All right, so remember our formula, uv minus the integral of v du. So I'm going to have u times v. So we'll have this x inverse cosine 2x. Minus the integral of v du. Since it's a minus and this has a minus, I'm just going to make that a plus. I'll go ahead and I'll pull the constant out and I'll have an x over root 1 minus 4x squared dx. All right, so as for this integral right here, if you look carefully, this one's going to be a perfect u-sub. If we let u equal 1 minus 4x squared, then our du is going to be a negative 8x dx, and negative 1/8 du equals x dx. So once again, it's a perfect fit for what's left right here. We're just going to have now this negative 1/8 sitting out there. All right, so we've got x inverse cosine of 2x. Now we'll have a minus 1/4 when we take that negative 1/8 into consideration. Integral 1 over square root of u du, and now we're at a point where we can simply add 1 and divide and then substitute this guy back in. So our final answer looks to be x times the inverse cosine of 2x minus 1/2 square root of 1 minus 4x squared plus c. And again, going from here to here was just a matter of adding 1 and dividing and then substituting our u back in there. Okay, so again, those inverse trig functions, guys, when you see them and there's not a perfect substitution, it's going to have to be done by parts, as we talked about. All right, so another example here, and you can see that there's really no way to avoid integration by parts. It's not a perfect substitution or any kind of manipulation or anything like that. So we'll go ahead and we'll start with our u and our dv. As I run through the list, inverses, no. Logs, no. Algebra, yes. The algebra would be the x squared, and then everything else has to be the dv. So moving down to our du, we get our 2x dx, and our v would be the negative e to the negative x. All right, so we've got our u times v, so negative x squared e to the negative x, minus the integral of v du. Because of that negative, and the negative originally out in front, we'll change that to a plus. We can also put that 2 there, and now we have an x e to the negative x dx. So we were at least able to whittle ourselves down from this into this. So if you think about it, how are you going to integrate that now? Well, another iteration of integration by parts should take it away. We got down from an x squared now to an x with this product still being here. One more cycle, and I think we've got it. So our u, in this case, would be an x to the first, and our dv would be an e to the negative x dx. Du equals dx, v equals negative e to the negative x. We still have this guy out in front, so negative x squared e to the negative x. And then I'm going to call it a plus 2, and then I'm going to put a big bracket there for a minute. I don't want this to get too overwhelming. So as I expand this guy out using our by parts, we have our uv. So that's going to be negative x e to the negative x minus the integral of v du. So we'll have a plus integral e to the negative x dx. And those brackets are there because of this 2 that I'm going to have to distribute. So this term looks pretty good. This integral is pretty easy. So I'm going to go ahead and distribute the 2 into both of those and integrate as I go down. So negative x squared e to the negative x plus, minus 2x e to the negative x. And then with the integral, we'll have a negative 2 e to the negative x plus c. So multiple iterations of integration by parts is not off the table. You can see that you're really at the mercy of whatever this secondary integral allows us to do. And in this case, it just made sense to continue the integration by parts process. And by doing so, got it down a little bit further into something we can integrate then directly. Okay, so we'll take a look now at e to the 3x times cosine 2x. And it looks to be a pretty familiar setup when it comes to integration by parts. We'll pick our u, we'll pick our dv to get started. So as I run through my list, I-late, inverses, no, logs, no, algebra, no, trig, yes. So this is going to be a cosine 2x, and then everything else has to be the dv, e to the 3x dx. So then our du would be a negative 2 sine 2x dx, and our v would be a 1/3 e to the 3x. Now you could do that off to the side by using a u sub, but I think by now we've all done these enough to know what that's going to go to pretty quickly. And so now using our formula, our uv, so that's going to be a 1/3 e to the 3x cosine 2x, and then minus the integral of v du. So because of the negative, I'm going to call it a plus. I'm going to have the constant 2/3 out in front with an integral of e to the 3x sine 2x dx. All right, so much like the last one, you're probably looking at this integral thinking, okay, we're going to have to go by parts again. And you're right. So setting it up again, very similar in fact, our u would equal sine 2x. Our dv would equal e to the 3x dx. Then for the du, we would have a 2 cosine 2x dx. And for the v, we would have our 1/3 e to the 3x. All right, so now let me go ahead and write this out. This is going to get a little bit longer, so I want to go and make sure I get everything that I need in there. So I've got my 1/3 e to the 3x cosine 2x, and then plus the 2/3. And like that last problem, I'm going to put that 2/3 all the way to the outside, and I'll worry about simplifying here in a bit. So then I have uv, so 1/3 e to the 3x sine 2x minus the integral of v du. So that's going to be a minus 2/3 integral e to the 3x cosine 2x dx. All right, so now before I even think about doing anything else, let me go ahead real quick and distribute this 2/3 in there. So as I do this, my 1/3 e to the 3x cosine 2x is the same, and now it's going to be a plus 2/9 e to the 3x sine 2x, and then minus a 4/9 integral e to the 3x cosine 2x dx. Okay, so we've got all that strung out, and now we're left with this integral. And so you're probably thinking again, well, let's go by parts. Well, yes, you would have to do that by parts, but you might even start to see what's really happening. We're just kind of going in a circle, right? In fact, the integral of e to the 3x cosine 2x is what we originally started with. So here's what we're going to do. I'm going to remember that this whole thing right here to where we are is equal to this. And so I'm going to set them equal. I'm going to go ahead and take the integral now of e to the 3x cosine 2x dx and set it equal there to what we have. And then I'm actually going to add over, since we have an equation, right? We can do the same thing to both sides. I'm going to add over a 4/9 e to the 3x cosine 2x dx. So I'm adding over a 4, my screen keeps popping up on me, there we go, 4/9 e to the 3x cosine 2x dx. All right, so on the right side, those go away. Over here on the left side, when I add 1 of these and 4/9 of these, when I add these going down, that's going to give me a 13/9 integral e to the 3x cosine 2x dx. And remember, that was still equal to all of this right here. So I'll have my 1/3 e to the 3x cosine 2x plus 2/9 e to the 3x sine 2x. And finally, if my goal is to get this integral all by itself, then I can just multiply by 9/3 and I'll have my answer. So if I take this thing and multiply both sides by 9, excuse me, I think I said 9/3, 9/13. So when I do that, I'll get e to the 3x cosine 2x dx equals, that's going to be a 3/13 e to the 3x cosine 2x plus 2/13 e to the 3x sine 2x, and then we can't go all this way without forgetting our plus c, right? So add that plus c on there, and we have our final answer. This is called circulating integration by parts. As I mentioned, it kind of felt like when we got to this point, we were going in a circle, right? We just ended up right back where we started. And once you hit that starting point, then just go ahead, set the whole thing equal to what you started with. Then it's a matter of adding it over to the other side, combining like terms, and then just dividing off that constant there at the end. So a really, really nice technique to save us from what otherwise would be just an infinite loop.